Uh, So hello, everyone. It's a great pleasure for me to introduce our speaker of ninth Enigma-Sleep talk, Professor Thanh Dang-Vu. He's a professor at Concordia University in Canada, and he holds a research chair in sleep neuroimaging and cognitive health. He is also an adjunct professor in neurology and neurosurgery at McGill University and vice president of Canadian Sleep Society. Today, as you see here, Tan will talk about sleep and cognitive health. We are collaborating on few Enigma projects together, mainly on sleep deprivation. And I'm really excited to hear your talk. Thank you for accepting my invitation. Stage is yours.
Thank you very much, Masoud, for the invitation. And hello, good morning, good evening, good afternoon, everyone, depending on your time zone. It's a pleasure to be here with you. I'm going to present you sort of an overview of our research program in my lab in Montreal. And you'll see that we cover quite a lot of different grounds, all on sleep and sleep disorders, and some research with a new imaging angle. But it's quite a broad program we have, spanning from basic sleep research to clinical sleep research. Okay, so just to start, my conflicts of interest. Since I'm not going to discuss about treatments, pharmacological treatments, so this relationship have no influence on my talk. And so this is the summary of the talk. So I'm going to discuss first some work we're doing, looking at slow oscillation and spindle coupling in relationship to memory consolidation. That's a topic that's been quite researched in the field lately. Then I'm going to move to sleep deprivation and present briefly the data set for which we're collaborating with Masoud, actually, some EEG-fMRI data about sleep deprivation and cognition. And also a newer study where we're looking at the effect of exercise on this relationship. Then we're going to move on the field of sleep disorders, and most of our research program sleep disorders focus on chronic insomnia or insomnia disorder, looking at its effect on cognition and the effect of treatment interventions on this relationship between insomnia and cognitive health. And finally, I'll finish with an example of new imaging consortium that we're trying to build around the central disorders of hypersomnolence, and show you some data we had collected in that field, and so what we plan to do with this consortium. Okay, so first, as you know, in sleep has been for now quite a while shown to be involved in memory consolidation during sleep. And there are, as you know, different scenarios behind this relationship, but a common one is the fact that memory traces are reactivated during sleep, in particular thanks to the facilitatory role of brain rhythms, in particular sleep oscillation, slow oscillation, sleep spindles, and shockwave ripples. And there's been quite an interest in looking recently at how the synchronization between these rhythms is actually essential to this consolidation of memory traces during sleep. So what we were interested in was to look at how it does affect memory consolidation in older adults, because as you know, with age, there's a cognitive decline that appears in some adults, and we wanted to know if this relationship between slow and spindle coupling is also relevant in older adults. So this is a study in which we recruited healthy older adults that were screened and then had one PSG night at baseline as a habituation night, and also a baseline night. And after 1 week, they had an experimental night. So during the experimental night, they were subjected to this declarative learning task, classic word pair learning task, where subjects had to encode these pairs of words in the evening. They had an immediate recall, and then after sleep, they have the delayed recall. And we're looking at the consolidation, which is basically the amount of pairs that were correctly encoded from that were correctly recalled from the morning to toward the evening to the morning. And so this is what we looked at in terms of signal processing. We looked at the EEG signal, this particular slow oscillation, and the sleep spindle. We were interested in their coupling, which can be measured in two ways. You can measure through the modulation index, which is the strength of the coupling, or the coupling phase, which is basically the distance at which they occur. So basically a sort of index of their synchronization. And here's what we observed. Basically, we wanted to look whether the learning happening the second night had an effect on this coupling compared to the baseline night, because right now, most of the evidence in the literature is looking at the relationship between coupling and learning without taking into account the baseline night. So what we observe is actually that there's no significant difference between baseline and learning night, which means that the learning itself doesn't induce a significant increase or change in the coupling in this oscillation, at least in healthy older individuals. So that's the first result. The second result, though, is that when you looked at the relationship between these measures of coupling and the consolidation of memories overnight, we found that while there was no relationship with the modulation index, there was a significant relationship with the change in coupling phase distance from the baseline to the learning night and the recall score. In other words, the more basically the spindle was shifted towards the upstate of the slow oscillation, the higher the consolidation score was overnight. So it really shows that the consolidation seems to be more dependent on how well they're synchronized rather than on the strength of this modulation. Okay, so that's basically, so that means that even though there's no consistent change in the coupling or in the coupling phase, those who had a better change in this coupling phase distance towards the upstate of the slow oscillation had a tendency to have a higher and better recall of memories. And it's a bit more complex than that because actually we found that there was an interaction between the coupling phase and the modulation index in such a way that when you had a high actually modulation index, the relationship between the coupling phase and the word per consolidation score was more significant. So even though the modulation index itself didn't have a direct relationship with how well people remembered the word pairs, it still influenced the relationship with coupling phase. So in conditions where, for those subjects who had a higher modulation index during the learning night, there was a steeper or more stronger relationship between coupling phase and memory consolidation. So basically what it shows is that we have a complex relationship where, in healthy older adults, there is some effects, but this effect is not induced, it's not reflected by consistent change after learning, but rather by relationship in such a way that those who learned better had displayed actually higher change in coupling phase during the learning night. And with this interaction with the modulation index. So now what we're doing is that we're pursuing this study in looking at what happens in older adults with who are not healthy. We have cognitive problems, and we're also looking at young healthy adults to see if these changes are different between young and older adults, and what are these changes across the lifespan. All right, so this is the first study, that's a pure EEG, looking at the mechanisms of the role of these brain rhythms in the consolidation of memory traces during sleep. Now, we are so interested in sleep deprivation. As you know, sleep deprivation is a leading cause of sleepiness during the day. We're talking here about, voluntary sleep deprivation, so not sleep deprivation induced by sleep disorder. And it's a leading cause of accidents on the road and so on. And so in this study, we were interested in looking at the brain imaging signatures of the effect of sleep deprivation on cognitive functions. And so this study, this is an EG-fMRI study data set where we recruited 20 healthy adults. All these participants had actually 2 MRI sessions. After they first have an habituation night where we screened out the presence of sleep disorders in the lab, and then afterwards they had 2 MRI sessions. One of the sessions was after a normal night of sleep. So in the morning, they had the scanner where they were scanned doing 3 cognitive tasks, which you can see here. The 3 cognitive tasks that were scanned were the attention network task, the NBAC task, or working memory task, and the PVT, the psychomotor vigilance task. And in the other session, they were scanned after undergoing a full night of sleep deprivation. That's what we presented in red. So they were subject to the same protocol. But then this session was longer because after being scanned out in the morning after sleep deprivation, they were allowed to sleep in the scanner to recover for a 60-minute nap opportunity, after which they were scanned again with the same task in order to see what happens in brain activity during the post-recovery nap when subjects were trying to undergo the same task. The objective of the study was to look at the effect of sleep deprivation on cognitive functions and fMRI responses to these cognitive tasks, but also to see how the recovery nap was able to restore these or change or basically return those activations to normal or not. And one of the questions we want to see also is whether there was a relationship between some of those fMRI responses and the behavioral effects on sleep deprivation. And that's what I'm going to show you now. And by the way, that's the data set that we agreed to share for the ENIGMA-Sleep consortium. And so the metrics that we were particularly interested in was the integration within and between networks. So, and we were particularly interested in looking at the functional clustering ratio, which is basically the ratio between integration within over between networks, which gives basically an idea of the mode of communication across the brain in that state. So the higher the clustering ratio is, the more local the communication is, and the lower it is, the more widespread the communication is in the brain. So these are the results on the left, on the right side. You can see the change in this functional clustering ratio across the different conditions. So in blue, the baseline state after a normal night of sleep. In red, the sleep deprived state. So not surprisingly, after sleep deprivation, there was an increase in the clustering ratio of response across the different networks. So basically, this sort of reflects this breakdown in functional connectivity when the individual is sleep deprived. So communication is more within than between networks. This is even more pronounced actually during the recovery nap, during non-REM sleep after the nap, after the sleep deprivation in gray. And finally, in yellow, as you can see, there is basically a partial return to a level that is somewhere between the sleep deprived and the well-rested state, where the function clustering ratio goes back to basically starts to goes back to a level that is similar to the well-rested state. So what it shows is that function clustering ratio really is sensitive to this change in vigilance across the different sessions. But now what we really wanted to see was to look at this relationship with these behavioral responses. And that's why it is, I think, very interesting. What you observed is that there was a significant relationship with both the accuracy and the reaction time across the 3 tasks, in such a way that the subjects that had the highest increase in function clustering ratio from baseline to sleep deprived were the ones that tended to have the most pronounced decrease in accuracy and increase in reaction time after sleep deprivation. That's what you see in the scatter plots on the top scatter plots. So accuracy on the left, reaction time on the right. You see that the more you have a decrease in accuracy, the higher the change was in the higher the increase was in the function clustering ratio, and vice versa for reaction time, because of course reaction time is inversely related to accuracy. So that's what we observed after sleep deprivation from relative state to sleep deprivation. And very interestingly, we observe the exact opposite relationship when you go from sleep deprivation to recovery, to post-recovery nap. So as I said earlier, so there was from sleep deprivation to recovery nap, there was a decrease again in functional clustering ratio, and the subjects that showed the strongest decrease in clustering ratio were the ones that increased the most their accuracy, and vice versa for reaction time. So that really shows that those changes in the clustering are so predictive. They're not only signatures of the vision state, they're also predictive of the subject's behavioral responses and behavioral basically in sensitivity to the cognitive sensitivity to sleep deprivation. So they show they're significantly related to how well or how bad they are impacted by sleep deprivation and how well they can recover after recovering now. Okay, so that's an example of the study that we've conducted with this data set. And we hope that is going to contribute also to the future papers of the ENIGMA initiative. So now what can we do in terms of sleep deprivation to alleviate its effect on brain function and cognition? So obviously ask people to sleep more, but that's sometimes not always possible because of different constraints, family constraints, professional constraints, and so on. And we're actually interested on the effects of exercise. And why is that? Because in the previous study that we conducted a couple of years ago, we actually showed that exercise was sort of synergistic to sleep in terms of consolidation of memory traces. So this is a study where we recruited young students, basically divided in 4 groups. And these 4 groups were basically subject to what they had to learn the class of tasks. And basically, they were either allowed to nap after the learning or to exercise before learning, or both. And you can see the 4 groups. So there are subjects who exercise before learning and napped after. One group that only napped, and one group that only exercised, and one group that did neither nap or exercise. And interestingly, what we observe is that the group that learned the task the best, that had the best recall of the learning task, was the group that had that were subject to, that were allowed to exercise before the learning. And this was actually a stationary bike moderate intensity exercise for 30 minutes, and then were allowed to nap. And this was better, significantly better than those who had only napped and those that only exercised before learning. So there seems to be this synergy between exercise, and we know that from other studies that exercise does impact sleep architecture and has increased the wave sleep, so wave activity. So it may be the case that this is something that can also sort of increase these or change sleep architecture in a way that is beneficial for memory consolidation. So we asked the question, well, if that's the case, can exercise actually sort of compensate or alleviate in part the effect of sleep restriction on memory consolidation? Because this has some practical concerns, implications. Some of us exercise sometimes in the evening, and is it actually a good, or is it actually a good thing when we're trying to learn, and particularly when trying to learn in a sleep-deprived state or before sleep deprivation. So that's what we tested. So we had in this study, so this is actually the study is conducted in two waves. So this is the wave that was conducted during the COVID pandemic. So this was conducted remotely. And right now we conducted the same study in lab, like in better controlled condition. But for this remote study, we had the subject divided in four groups. One group that had a normal 8-9 hours sleep opportunity and that learned the task before and recalled after sleep. A group that had a high intensity exercise before the average sleep opportunity. A group that was sleep restricted to 5 to 6 hours to mimic the sort of social type of sleep restriction that people encounter when they had to work or when they have social activities or family constraints. And then a group that had high intensity interval training before the sleep restriction. So this is basically the protocol. So this was a remote intervention. So they had an exercise program, which I'm going to show on the next slide. And they were monitored remotely through the intervention by kinesiologists. And as you see, so two of the groups had this HIIT session, high intensity interval training session around 7 p.m. The other groups did not, and they had to sit down and remain still for these 15 minutes. And then afterwards, they had this learning task and coding, which was actually a face name association task, immediate retrieval, and then they were sleeping either in a 8 to 9 hour sleep opportunity or a restricted sleep opportunity before being retested in the morning. Okay, and so this is the exercise that they were conducting, that they had to do. So it's a 6 body weight exercise, conducted, repeated 3 times. You can see that, these are all body weight exercise. It's no weights, no need for equipment. So squat jump, shoulder tap, lunge, burpees, mountain climbers, etc. And this lasted a total of 15 minutes at high intensity. And why high intensity? Because I also want to mimic this short exercise that you can only do, or that you can do when you have are very busy. You have like 1 hour to exercise. What is the effect of this short and high intensity interval training? So now here are the behavioral results, and that's interesting. So this study was conducted in 92 adults. These were mainly young individuals, students, for the most part. So you can see that. So in the first column on the left, when you have a sleep restriction, you had a lower recall of these memory tasks compared to when you are normally rested. That's the second column, and this was a significant effect of sleep restriction. But now what is, I think, very interesting is that when you looked at the third and fourth column, what you can see is that after exercise, after the high intensity interval training, there was no more significantly different effects on performance compared to the well-rested group between those that conducted high intensity interval training before learning. So you can still see that there seems to be some effect, but this effect is not significant. So what it shows is that there seems to be, as we did expect, an attenuation of this memory effect by sleep restriction that happens with exercise. So exercise partially attenuates this disruptive effect of sleep restriction memory recall, according to this data. So I think that has a very important implications. It shows that it's actually, if you insect exercise may be actually in a way to sort of when you don't have a full night of sleep, make your sleep less impacted by sleep restriction, with all the potential public health implication it has. So, and that really illustrate that sleep is not the only thing. Exercise and sleep are two pillars of a good health, and you should favor both. But if you can't, then I think exercise can also be some important aspects of the equation. And so, as I said, right now we're looking at the effects on sleep architecture by doing an in-lab, well-controlled study. All right, so where am I on time? Okay, 25 minutes. Good. So now I'm going to shift to the third area of our research program, which is an insomnia disorder. Insomnia disorder, as you know, is very frequent, and we are particularly interested in the effect on cognitive functions. And as you know, as we age, insomnia symptoms increase, and we will and also actually insomnia increase in people with cognitive impairment. So this is just to show some data from the Quebec cohort that we have, where we looked at subjects with subjective cognitive impairment, mild cognitive impairment, and even dementia. There are some sleep assessments in that cohort. And you can see that, of course, the cognition, the Montreal Cognitive Assessment, the MoCA, is significantly decreased in people with MCI. But what you can see here is that when you look at the prevalence of insomnia disorder according to the DSM-5 or ICSD-3 criteria, there is an increase in MCI compared to SCI in healthy controls, healthy older adults. Now, in these samples, 20% of the MCI had some questions that are compatible with insomnia disorder. And this is in line with this progressive increase also in the insomnia severity index along the cognitive deterioration from healthy to subjective and to mild cognitive impairment. Okay, so this just illustrates some fact that is known that prevalence of insomnia symptoms and disorder increase with cognitive decline. Now, what we were really interested in is to look at the inverse relationship. Okay, we know that with cognitive decline we have increased insomnia, but does insomnia predict a higher rate of cognitive decline with age? So can insomnia be not only a consequence of the cognitive disorder, but also a predictor of the cognitive disorder, a risk factor? So these I'm going to show you two studies we conducted on the CLSA, the Clinical Longitudinal Study in Aging, which is a large cohort of almost 30,000 individuals recruited across the country from eastern to western provinces. And they are followed up for, well, it's expected to be followed up for 20 years. We're now at the second follow-up. There's a follow-up every 3 years. And what's very interesting with this cohort is that they have a really comprehensive set of assessments. They have not only questionnaires, but also a physical examination, biological samples, and a quite complete neuropsych test battery. And fortunately for us, they also have some quite detailed sleep questions on insomnia, sleep apnea, RVD, and other sleep disorders. And in terms of insomnia, there are questions that really looked at each type of symptom of insomnia, so sleep initiation, sleep maintenance problem, their duration, onset, and the impact on daytime function. And so thanks to this question, from this cohort, we're able to identify individuals who had no insomnia symptoms, represented in green here, those who had insomnia symptoms only, which means that they complain of difficulties falling asleep or staying asleep, but not for long enough, so not for more than 3 months, and not having any daytime impact of these insomnia symptoms. And then in blue, you have those who have a probable insomnia disorder, which basically means that they fulfill the criteria for insomnia disorder according to DSM based on these self-reported questions. And the first study that we published was to look at the baseline data, to look at the association between the presence of insomnia disorder, insomnia symptoms, and the results of the different neuropsych test battery. Because the question we asked was, is insomnia associated with worse cognitive functions? And this took into account all the other factors that you see in the middle that can affect cognitive functions. And when we took them into account, there's still a significant effect of probable insomnia disorder on one test, on the memory test, which was the RAY auditory verbal learning test, where not insomnia symptoms, but probable insomnia disorder, people had a lower recall or a lower memory recall to the others. So what this firstly shows is that when looking at cross-section data, insomnia disorder is associated with worse memory performance. And this was the domain that actually was significant. And now, in a follow-up study we published last year, was to look at the longitudinal study, so the change in insomnia status from baseline to follow-up. So by looking at the follow-up, we're able to basically group people with insomnia, group people from the baseline according to 3 categories. We only took at baseline those who had no insomnia symptoms whatsoever. And then we looked at whether they, after 3 years, they remain without insomnia problems, or they complain of insomnia symptoms, or whether they developed an insomnia disorder according to the same questions. And basically, we looked at whether this evolution into one of those 3 categories was associated with different memory problems. And this is what we observed. We observed that actually the development of insomnia symptoms only in green was not significantly associated with any memory problem, but the development of probable insomnia disorder was associated with, in blue, was associated with increased odds of having a memory problem diagnosed by a physician, or, and that was a odds ratio of almost 3 to 2.72, or having a self-reported subjective memory worsening with an odds ratio of 1.72, significant enough to take into account all the other factors that can affect this relationship, including, by the way, we looked also at sleep duration, because I know that's a lot of interest on what is sleep duration does affect, and we didn't find actually a relationship for sleep duration. So it's, but the development of insomnia disorder does, we found that it does increase the odds of subjective memory decline and memory problem diagnosed by a physician. So from this longitudinal study, we concluded that participants who developed insomnia disorder with time showed higher odds of subjective memory decline, even after adjustment for comorbidities, which really highlights the fact that insomnia disorder is not only a consequence or a symptom of a cognitive or neurodegenerative disease, but may also be a risk factor that predates the development of cognitive decline with age. And in that sense, it should be an interesting risk factor to target in future trials. And so that's another part of the research we're doing right now, is to actually see how different insomnia interventions affect cognitive health. So I'm just going to show one study that we published, because there are actually a few trials that we're running right now to look at that in more details. But as you know, the main treatment for insomnia is cognitive behavioral therapy for insomnia, CBTI, which is the first-line treatment for insomnia disorder. And so the aim of CBTI is really to target factors that perpetuate insomnia over time, so cognitive and behavioral factors that may make this insomnia perpetuate over time. And the classical format of this is to look at group therapy or individual therapy for 5 to 8 sessions, 1 per week. And it's been shown to be actually quite efficient, because 60% of people usually respond to CBT, and 40% show remission of CBT. Okay, so in that study, this first study published last year, we looked at the effect of CBTI. That was a trial, randomized controlled trial with CBTI versus waitlist for 3 months. Afterwards, they had a second visit, and not surprisingly, as expected, CBT had a significant effect on ISI in such a way that only the CBT group after the second visit had a decrease in insomnia severity index, not the waitlist. But then we wanted to look at the effect on subjective versus objective measures of sleep. For example, if you look at the effect on sleep efficiency, CBT increased sleep diary sleep efficiency significantly over time, but not the sleep efficiency that we measured in the lab with polysomnography. And that's actually in line with other papers that show that the effect of CBT is more predominant on subjective rather than objective sleep variables. But what is really interesting, though, is that we found that we're interested in this metric that is called sleep perception, that some of you may know. So that's basically the difference between what people report about the sleep times versus what is actually measured either in lab or at home with an objective instrument. So in this case, it was PSG. And so what we calculate is the sleep misperception, which is the difference between, for example, in this case, total sleep time. reported by subject versus what was measured by personography. And it's very common. It's actually been shown that people with insomnia disorder on average, they tend to underestimate the sleep time. And in this particular data set that we published, they underestimated sleep time by approximately an hour compared to what the PSG showed. And what is really interesting is that the CBTI treatment, and not the waitlist, improve this perception of sleep in such a way that after treatment at T2, you see that the difference between objective and subjective source sleep time was no more significant. And that's what you can see in the solid line on the right graph. So what it shows is that CBTI does not only improve subjective sleep quality, but also improve sleep perception in such a way that people are better able to estimate their total sleep time compared to what the objective recording shows. So that's what we showed here. So CBT improves subjective perception of sleep, and that was also valid, by the way, for not only sleep efficiency, but also time spent awake, so also sleep quality and sleep latency, and reduce the discrepancy between subjective and objective measures. And what about cognition? So in this particular trial, this trial was based on, was conducted on adults that had a quite broad age range from 20 to 70 plus years old. So in this very heterogeneous sample, we didn't find actually a lot of cognitive effects. In terms of self-reported cognitive function, we show that there was a trend for lower self-reported cognitive impairment after CBT, but this was not significant. And in terms of cognitive function, this particular study, we only had two measures. We only had the NBAC, working memory, and the ANT, in which we didn't show any effect. But we didn't have, for example, a measure of memory, which is shown to be the most sensitive to insomnia. So what it shows is that, with this limited test, we didn't find an effect, but we probably need to test more cognitive functions. And also what we're interested in now is really to look at subgroups of individuals with insomnia or older adults and have subjective cognitive complaints, because those are the most vulnerable to cognitive functions, and they may be those who are the most sensitive to the effect of treatments in terms of cognitive function. So that's what we're currently investigating now. Another development that we're doing now is to shift from in-person CBT. So this trial that I showed you was conducted with in-person CBTI with a one-to-one session with psychologists. But now we're shifting to a format where we looked at online CBT. Why is that? Because as you know, CBT, it's great, it's working well, but it's really difficult to access in most countries. At least in Canada, it's not covered usually by the public healthcare insurance because there's very few public insomnia clinics. So you have to go to a psychologist and pay, for whole program, $500, $600, $700, or even more sometimes to have the whole program covered. That's not accessible for most people if you don't have a private health insurance. And secondly, some people don't want to just make the effort of going to see a psychologist and connecting at specific times. So development of online programs offering CBT is trying to address these issues by having a platform that a person can access at any time at their convenience and with a low cost or no cost, depending on the situation. There's been studies showing that both types of CBTI have an effect, and even though the face-to-face may have a larger effect size than online CBT still have a significant effect, significant response on insomnia and sleep quality. So we developed a program in my research center, which is called the eSuite for the Promotion of Healthy Aging in the Community, which is a web platform aimed at disseminating multimodal prevention intervention programs. And that's basically the interface. Now it's available both in French and English. We just completed the translation. And basically, as you can see right now, it covers 4 domains. It covers nutrition, communication, memory, and sleep and mental health. And in terms of sleep and mental health program, it's sleep and mental health because our CBT program in that particular platform involves both CBT, but also CBT for CBTI for insomnia, but also CBT for anxiety. Why is that? It's because insomnia and anxiety are highly comorbid, especially with age. So, like, at least 1/3 of people with insomnia has also some comorbid anxiety. So it did make sense to us to address both problems in the CBT program in order to be as efficient as possible in addressing sleep problems with age. So this is the content of the program. It's actually now been extended to in a new version that we are currently testing. We also include capsule on depression, and it's not 7 but 10 capsules. But this is I'm going to present you some preliminary data on 7 capsules where you show that it affects cognitive psychoeducation, anxiety, insomnia, cognitive restructuring, reducing insomnia, and so on. So the main cognitive and behavioral components is just example of snapshots of these modules that have some visual content and also audio content where people can listen to a voice that just explains them the different steps. It's made in a way that is visually attractive and simple to understand. So we had the e-learning specialist really building this capsule with us to make them as attractive as possible. As I said, it's also available in English. So you can see first, this is, for example, psychoeducation insomnia. We explain sleep cycle, sleep stages, what is insomnia. And we also go through different sleep hygiene elements, about caffeine, bedroom, physical activity, and so on. And the bottom, you see also an example of when we explain stimulus control, so behavioral strategy for CBT. And at the end of each capsule, there's a quiz in which people will be tested on their knowledge, and they will have an immediate feedback on the answer, whether it's wrong or right. If it's wrong, then it will be explained why it is. And so this is just trying to present to you the first validation study that we conducted on 92 participants. They were randomized to CBT online versus waitlist for 7 weeks. And we only looked at, it was all conducted remotely. This was during COVID again. So we were able to look at the effects on insomnia and sleep and anxiety variables. And what you can see is that there was really a significant effect of this program on ISI, with a significant decrease in ISI only in the eCBTI group, not in the waitlist group. And this was also actually reflected when we looked at anxiety symptoms based on the anxiety inventory, some effects. So a significant decrease in the anxiety symptoms compared to the waitlist. And when we looked at sleep diary sleep efficiency, they can find the platform. We also saw an increase in we saw a significant effect of CBT, where there was an increase in sleep efficiency in the CBT group compared to the waitlist group. So what it shows is that this platform is working in older adults to improve their insomnia and anxiety symptoms. And we're now testing its effect on various cognitive functions to see if it also holds promise in preventing or promoting cognitive health with age. So this is what I wanted to discuss with you about the insomnia program that we conduct in our lab. And then last, I'm going to show you a very quick overview of our program now that is dedicated on not insomnia, but central disorders of hypersomnolence, so the opposite problem, so people having excessive daytime sleepiness. And among the cause of excessive daytime sleepiness, the main cause is sleep deprivation. The second cause is sleep apnea. But and then you have the central disorders of hypersomnolence, which are less frequent, but also very important and less understood. This is the case of narcolepsy with cataplexy, without cataplexy, and idiopathic hypersomnia. There's been actually quite a few imaging studies looking at the effect of narcolepsy with cataplexy on brain imaging, both from structural and functional studies. And what these studies have shown is that narcolepsy with cataplexy results in a change in gray matter volume and thickness, particularly in the hypothalamus and a variety of cortical areas. And that's also reflected in functional imaging when looking at glucose metabolism, blood flow, or fMRI responses, which decrease activity in the hypothalamus and a variety of cortical regions are supposed to be the reflection of the projection of the hypocretin, because what we know now from a lot of studies is that Narcolepsy with kataplexy involves a deficiency in the hypocretin system, which is this neurotransmitter produced in hypothalamus that projects to a variety of regions to activate the system, and then a default in the hypocretin system will result in daytime sleepiness in those patients in narcolepsy cataplexy. But the question we asked was actually what happens in those patients with narcolepsy without cataplexy? Because right now, if you look at the ICSD grouping of sleep disorders with central nervous disorders, we have narcolepsy type 1 with cataplexy. Cataplexy, for those who don't know, is this emotion-triggered loss of muscle tone. So it's usually very positive stimulation like a laughter or a joke or a happy surprise that will induce this muscle tone, this muscle atonia. It can be the whole body or just the face or the arm, and that's going to be usually quite spectacular in manifestation. But that's basically a typical type of narcolepsy that we call narcolepsy type 1 or narcolepsy with cataplexy. Now there's a portion of patients who have the other criteria of narcolepsy, particularly the sleep onset REM period. So those patients with narcolepsy, they usually enter REM sleep rapidly when they fall asleep, but they don't have cataplexy in it. And that's why they're called type 2. And there's also another phenotype of patients who have been called idiopathic hypersomnia. So these are patients who have also excessive daytime sleepiness, but some of them have a very long sleep time. So they can sleep for 12, 13, 14 hours, 15 hours at night without feeling refreshed in the morning, which is different from narcolepsy patients. Narcolepsy patients actually tend to have a fragmented sleep. They tend to wake up a lot during the night. And that can be, and that actually contrasts with the fact they're sleeping during the day. IH patients, idiopathic hypersomnia patients, usually don't have this problem. They can sleep for a long time. Some of them sleep for a normal time, but what's common to patients with IH is that they have an unrefreshing sleep. Even if they nap during the day, they will still be very tired. While narcolepsy patients usually tend to have refreshing naps. So there's been now, first, there's not a lot of evidence about what basically happens in the brain function, brain anatomy in those patients without narcolepsy type 2 and IH. And there's actually not a lot of evidence why narcolepsy type 2 and IH should be separated, because besides a few specific clinical features, which are not always consistent, there's not a lot of evidence behind the distinction of those two categories. So there's actually now a certain number of colleagues who say that those type of disorders should be reassigned in classification, with type 1 staying as a one category, and then another category with being narcolepsy spectrum disorder with patient with IH and narcolepsy type 2. And those idiopathic hypersomnia with long sleep time may constitute the third category. So that's basically a discussion around that. And to basically provide evidence for this discussion, we actually need to have scientific evidence. That's why imaging plays a role to try to see if there is some specific feature for each of these conditions. So a couple of years ago, already we published the first brain imaging study of patients with idiopathic hypersomnia. We did a SPECT study and then also an MRI study with structure and function sequences. And the SPECT study looked at changes in blood flow in those patients at rest after sleep. And what you observe actually is that patients with idiopathic hypersomnia have a decreased blood flow in several regions, but particularly in the anterior cingulate cortex and the putamen, and also an increase actually in the amygdala and temporal occipital regions compared to healthy controls. So, and as you can see, so those decreases in blood flow mostly happens in areas of the default mode network. And what is very interesting is that when you looked at this distribution of changes in blood flow, that resembles quite a lot with what we observed when normal, healthy sleepers fall asleep. So from previous PET studies, we had shown that in good sleepers, in deep sleep compared to wakefulness, there's a decrease in the same region in the medial prefrontal cortex, anterior cingulate cortex, and precuneus, and also putamen compared to wakefulness. And that resembles the distribution that we observe in idiopathic hypersomnia patients during wakefulness. This made us think whether this made us think that maybe actually one of the features of IH is that they have this state of where the metabolically the brain is not completely awakened. So there might be a sort of an incomplete sleep to wake transition, whereas the brain remains in a state that resembles deep sleep, even though the patient is awake. And this may explain why those patients are always sleepy and have this unrefreshing sleep when they wake up. And in terms of MRI studies, we actually looked at the differences. We show some effects that were actually quite in line with what the SPECT studies show. First, in terms of functional connectivity, we looked at functional connectivity within the DMN, the default mode network, and we found that there was a decreased connectivity within the DMN between nodes of the DMN and the inferior frontal gyrus here, as you can see, in patients with IH compared to good sleepers. And in terms of anatomical imaging, we actually observed the opposite, which is interesting, but we observed greater cortical thickness, but this cortical thickness increase was limited to areas of the default mode network, particularly the prefrontal gyrus and the posterior cingulate cortex, which makes us think that maybe these areas that show decreased blood flow, decreased connectivity in these patients actually display over time an increased cortical thickness as a sort of a compensatory mechanisms to chronic sleepiness state. So right now what we're doing is to see what are the specific features of NT1, NT2, and IH, the sleep restriction. That's a multi-center study that we conducted over 2 sites, our site in Montreal and the sites of our colleagues in Amsterdam with Dr. Isvan van der Werf, Ralf Ronzek, and Gertjan Lammers. This is just a very preliminary set of results I show you just to show you an example of what you can look at. And the goal is really to have a study that systematically compares NT1, NT2, IH, and healthy controls. Because right now, most of the data that is available is about NT1, or there's a couple of reports that looked at NT2 or IH, but there's no report that looked at the systematic comparison between these different categories of disorders. And what we looked, for example, was to extract hypothalamic volume. And in this preliminary analysis, what you observe is that idiopathic hypersomnia patient and NT2 patient had somewhat of a decrease in the volume of hypothalamus, but the only significant decrease was with patients with NT1, and that's in line with what we know from the literature about the effect on the hypercretin system. On the contrary, when you looked at other areas such as the amygdala, we found some sort of more generic decrease in the volume across the 3 groups of patients, which suggests that there might be some signatures of brain functional structure that's specific to NT1 and others that are common to all 3 types of disorders. So the goal is really to identify what is specific and what is not specific across the 3 disorders of hypersomnolence. And to make this effort more significant and robust, we've started to build a consortium hypersomnolence disorder, which we call NICHI, for Norwegian Consortium on Central Disorders of Hypersomnolence, where we receive support from different companies actually to allow us to do this. So we established a steering committee with colleagues that you can see here, with 2 also very excellent PhD students, Yari and Eva on the right, that run most of this analysis. And we've made contact with a variety of countries and centers. We have imaging data of patients with narcolepsy and IH. And we're now at the stage where we're trying to come up with the data sharing agreement to allow this to happen. But if we are able to conduct this analysis, we have a much better, stronger sample size, because with the different sites combined, you can have up to 500 or 600 patients per group, a bit less for NT2 and IH, but these are still numbers that are growing as we collect more data. So that really is our goal in the next future, to have more robust results on this group of poorly understood disorders. So I have no results to show yet today, but that's really work in progress, and I hope I can show you results in the next year or so. So that's the end of my talk, and I see that I've talked already for 55 minutes. I'm sorry, a bit longer than I thought. But if I want to summarize what I showed you today, I showed that there's a shift in slow wave spinal coupling towards the upstate that predicts memory recall in older adults. I showed you that measures of brain integration predicts cognitive vulnerability to sleep deprivation, and also recovery after a nap. I showed you that exercise can attenuate the effect of sleep restriction on memory recall. I showed you this bidirectional relationship between insomnia and cognitive decline, where insomnia is more frequent with cognitive decline, but may also be a risk factor for the development of cognitive decline with age. CBT reduced the discrepancy between subjective and objective measures of sleep. Online CBT for insomnia anxiety improves both self-reported sleep and anxiety outcomes in older adults. And finally, brain imaging can identify structural and functional patterns that are specific to narcolepsy and IH. And future studies will hopefully consolidate these findings. All right, so I know it was a lot of data to show you in less than an hour. I just want to acknowledge my team, the SCN lab, my research associate, postdocs. Some of them have moved out now, but they run those studies. My teams of grad students, research coordinators, CIPTEX, and all my collaborators across the world, and then my funding agencies that funded all the studies I showed you today.